In this video, we will talk about how to do integrals that involve powers of tangents and secants. So remember, we have this trig identity, which says sine squared theta plus cosine squared theta equals 1. There's a really similar trig identity that involves tangent squared that you've likely seen before, but let's recall, how do we get that identity? Well, we just take this first one and you divide both sides by cosine squared theta, because sine squared theta divided by cosine squared, that gives us this tangent squared. Cosine squared divided by cosine squared, that gives us this plus 1. And on the right side, 1 divided by cosine squared, well, that's going to give us secant squared. And this is where this trig identity comes from. So you might recall this identity, but this is how we get it. So, okay, let's look at an example. Let's say I want to do the integral of tangent to the 8 theta times secant of the fourth of theta d theta. Just like we saw in that last video when we did integrals involving powers of sines and cosines, often we are going to try to do a u sub. And for u subs, we need to recall some of the basic derivatives. So like for these, what's the derivative of tangent? What is the derivative of tangent? Well, that is just secant squared. So secant squared theta. And then what is the derivative of secant? So the derivative of secant of theta is secant theta times tangent theta. Secant theta times tangent theta. So, when you have tangents and secants in your integral, the most natural choice for you is either to let it be tangent or to let it be secant. If I was going to let u be tangent for this integral, then du would involve secant squared. So it would be super nice if instead of having secant to the fourth, if I just had secant squared, because that would work perfectly. So if I can somehow split out a secant squared out of this, and then everything else is just tangents, that would be awesome. So let's try to do that. So I get the integral, I have that tangent to the 8 in front, and then let's split up the secant to the fourth as a secant squared times another secant squared. Secant squared times another secant squared. Okay, so I'm just doing a little algebra there. D theta. So that secant squared at the end, that would be so nice if that could just become du. But to make that happen, everything in front needs to have tangents. I don't want this secant squared to stay as it is. And that's where I can use this trig identity and replace it with that tangent squared plus 1. So I'll get the integral of tangent to the 8th of theta, replace that secant squared with tangent squared theta plus 1, and then times that other secant squared that we split out, d theta. And now this is going to be awesome for a u sub. So let's do u sub. Let's let u be tangent theta. Then du, its derivative is going to be secant squared theta d theta. Okay, and I'm going to highlight that because I see that in the integral now. I see secant squared theta d theta. That is here at the end. So that's going to become du. So when I sub in, this first part becomes u to the 8, parentheses times u squared plus 1. And then the highlighted stuff just became du. Okay, so I've converted it to u's. Now I can distribute u to the 8 to get u to the 10th plus u to the 8. And now this is something that I know how to do the antiderivative of. I just do my reverse power rule. So add 1 to the power to get u to the 11, and then divide by that power, 11. Same thing for the next term. I get u to the 9 over 9, and then I put my plus c. Now I got to plug back in for what u was. So that'll give me tangent to the 11th all over 11 plus tangent to the 9th all over 9. And then I got my plus c. And there we have it. There we have our antiderivative. So the key again to making this one work was the fact that I could split out this secant squared theta was going to make a u sub work really nicely as long as I can convert everything else to be in terms of tangent. And I was able to do that here. So that when I made my u sub and let u be tangent, well, du was secant squared theta, d theta, and I had already split that out at the beginning. So that made this u sub work out perfectly. Okay, so let's look at another example. Let's say I have the integral of tangent to the fifth times secant to the seventh. Okay, so with this one, I'm first going to notice that, like, what if I tried doing the same type of thing? Let's split out a secant squared. So let's write this as tangent to the fifth, and then let's rewrite that secant to the seventh as secant to the fifth theta times the secant squared, like we did before, times the secant squared. And then d theta, of course. So to make this work, this part at the beginning, I need to write completely in terms of tangents, so that when I u sub for that, the part at the end with secant squared will be du. But the problem is, for this trig identity with secant squared, I can make this work as long as the power of secant is even. Like, for example, if I had secant to the fourth, I just square both sides of this and I have secant to the fourth. But secant to the fifth, well, that's an odd power. And that's not going to work so nicely. So I really need an even power on this secant to be able to use this identity. So because of that, just splitting out the secant squared isn't going to work as well as it did in that last problem. So what if instead we try to leverage the derivative of secant, which is secant tangent? Maybe let's try to split out a secant and a tangent. So I will split out a tangent from the tangent to the fifth. That leaves me with tangent to the fourth. And I'll do that from the secant, split out one secant, which leaves me with secant to the sixth. And now I'm splitting out one tangent, which I'll write at the end, and one secant, which I'll write at the end. Okay, and then I got my d theta. So again, what I've done is I've rewritten tangent to the fifth as tangent to the fourth times a tangent. And secant to the seventh, I've rewritten as secant to the sixth times another secant. Okay, so I'm really hoping to make this tangent theta, secant theta at the end part become my du. But for that to work, I need everything before that to just be in terms of secants, so I can u sub for secants. So I'm going to need to convert these tangent to the fourth term to secants. So I can use this trig identity if I first notice, oh yeah, tangent to the fourth is tangent squared getting squared. And now I can sub in for that. Tangent squared is secant squared minus 1. And that whole quantity is getting squared. And now let's u sub. Now let's let u be, let me write that better. Let's let u be secant theta. So that du is secant theta tangent theta d theta. Okay, now I'm seeing that du is here at the end. So when I sub in, I'm going to get the integral of this first part becomes u squared minus 1 in parentheses, that whole quantity squared. Secant to the sixth is u to the sixth. And then the whole thing at the end becomes du. Okay, so I've converted it all to u's. But to evaluate this whole term that gets squared, I have to FOIL and expand that out. So doing that, I get u to the fourth minus 2u squared plus 1. Then I can distribute u to the sixth into that. So that gives me the integral of u to the 10th minus 2u to the 8th plus u to the sixth. Okay, now we are ready to do this antiderivative. This gives me u to the 11th over 11 minus 2u to the 9th over 9 plus u to the 7 over 7 plus c. And my last step is to plug back in for u. So doing that, we get secant to the 11th of theta over 11 minus 2 secant to the 9th of theta over 9. And then plus secant to the 7th of theta over 7. And then plus c. And we got it. We got it. So to recap some of our takeaways from these two examples before we end with one other one is, When we have these integrals that involve powers of tangents and secants, my goal is to try to either separate out a secant squared theta, d theta like this, and then to get everything else to be in terms of tangents, because then it's really nice if I let u be tangent. Or to separate out a tangent theta, secant theta, and if I'm going to do that, to get everything else before it to be in terms of secants, because if I can do that, I'm going to let u be secant, and that'll work out really nicely. Okay, so let's end with a different flavor of example. Let's do the integral of just secant of x. Okay, we've learned at this point how we do the antiderivative sine, how we do the antiderivative cosine. Those were kind of like the basic ones. We've also seen how to do the antiderivative of tangent and cotangent. Those involve kind of a simple u sub. The antiderivative of secant and cosecant are actually significantly more complicated. One of the reasons why is, one of the ways to do the antiderivative secant is it involves a very genius step, something totally not obvious, which is to first multiply the top and the bottom by secant x plus tangent x. And then to do u sub. I'm going to let u be secant x plus tangent x. And if I do that, then du is secant x times tangent x plus secant squared x dx. And why that's nice is now in the numerator, if I distribute secant x to each of these terms, that just becomes du precisely. So the numerator just becomes du, and the denominator is just u. So we get the integral of du over u, but that's just natural log. That antiderivative is natural log absolute value of u, and then plus c. Now I just got to plug back in for u, and I get natural log absolute value of secant of x plus tangent of x. Close it, and then plus c. And that's actually my antiderivative of secant of x. So I'm going to box this. Okay, so we will ultimately learn another way to do this that doesn't involve such a genius step. It involves, I think, kind of much more natural things that we might be able to reason out. It also involves a method that we'll learn later in our class called partial fractions. So we will work that out on the homework later in our course.